so I'm going to look at 402 now in the RSA section. And that's here. So we're going to crack a short RSA key. So here's RSA. Now to make an RSA key, you make a public key and a private key. And you do it by choosing two large prime numbers and multiplying them together to get n. And that is the main part of the public key. The other part is E, which can always just be a number like 3 or 65537. A small prime number is fine. And that's all you do for publishing the public key, which other people will use to send you a message. But when you decrypt it, you have to find the decryption key, and you get that from phi of n. And then you compute the private key so that d times e is 1 mod phi of n. And that will cause your raising things to the power d to undo the encryption operation. So the whole point is, if you have a public key, nobody should be able to find the private key from your public key. But as we said, that is only true in practice if your public key is long enough. And now people recommend at least 2048 or 3072 bits. So here we got a public key that is what looks like about 15 digits. So that's only about 40 or 50 bits. So it's far too short to be secure, and that's the point. So let's see if I can do it here. If I have Python 3 minus m pip install, I think I've already got it on my Mac, but let's see, install PyCryptoDome, which is what I learned from CryptoHack as the new cool cryptography library to use. And could not find a version. All right. So maybe I should be using my Linux machine. Let me just do that. Python is different on the Mac. Did I misspell something? PyCrypto. Oh, I did. Why, thank you. Good. Maybe I don't need to use a. Good. It's already got it. I thank you. Good. Then I don't need to use Linux after all. Good. Good. I appreciate the help. So now I should be able to factor this number. So I should be able to do this jazz. And let me just, there, this will do. I can shove both of these out of the way. All right. All right, so Python 3. Okay, so I import math. I set n equal to that, and now I get the square root. And you can see I get this number. And that's only to a certain number of decimal places, but it's probably good enough. So now I know approximately what the square root is. And here is what you can do. Now, in principle, I would have to do, if I wanted to do, this is 100 million, essentially. So if I might have to try 100 million guesses to find a number that would factor this, to break it up, because I know this n is the product of two numbers. And 100 million is not that large a number. I could do it, but what I'm going to do is I'm going to start from this and go backwards. Start from the square root and go down. And that's a fun way to do it. So here, I'm going to start from that number, 100, 7, 11, 415, and I'll go down to 413. I might as well, because 415 is clearly not prime. And I only need to try the prime numbers. So I'm going to only do the odd numbers below 413 because it's too much bother to prove that numbers are prime, but I know that the even numbers are not prime. So I'll be starting at this number and then jumping down by twos until I've gone down to 40 numbers below that. And so here's the product of n%i. This is n modulus I. And if I get a result of 0, that means it divided it, and I did. So that means this number here is p. And I can verify that by setting p equal to that, and then calculating the integer part of n over p. That'll be q. So this is p, that's going to be q, and to verify it, I can take p times q and compare it to n, and then take n minus p times q, and as you can see, I've done it. So in this case, since you chose two prime numbers that were very close together to make n, they were both very close to the square root of it, and therefore you can find them very easily. That's why you should choose two random P and Q that are not necessarily close to each other. And you see they are very close to each other. There's 1 to 10, 14, 2, 7, 8, 9, 3, 1, 2, 7, 2, 5. This is 007. And here's the P and Q. 100, 7, 11, 409, and 100, 7, 11, 423. They're only apart by like 14 here. And so in that case, it's not secure at all because it's too easy to find P and Q. All right. Anyway, so now I've found P and Q. So now I can find the decryption key. So phi of n is P minus 1 times Q minus 1. And so this is phi of n, that number, which is a little bit smaller than n, because n is P times Q, and this is P minus 1 times Q minus 1. Now we have to find the private key D, the multiplicative inverse of E. And we know that the E is 5 because we were given the public key, and the public key was this, which is n, and they're using 5 for E. You typically choose a small prime number for E, and 5 is fine. So we know E, and we need to get the multiplicative inverse of E mod phi. And that's a little bit difficult. You can do it with the PyCryptodome library. There is a fast algorithm to find it called Euclid's algorithm, where you have successive guesses that get there. And it's not that complicated, but in fact, they already included it in the PyCryptodome library. They gave us a function called inverse that will do the modular inverse. So we'll do the modular inverse of E mod phi. So that's all you got to do. Take it from CryptoUtil. And now it will find it for you. I found D as the inverse, which is this number, 8, 11, and all that jazz. And here's E, and to test it, I take D times E mod phi, and that's 1. So this is the multiplicative inverse. So now I have the decryption key. So now we can encrypt a message. If we want to encrypt the message high, we'll just turn those HI exclamation point into numbers by just taking the ASCII code for them, which is what the OR does. And then I'll turn it into one big number by taking the first thing times 256 squared, the next thing times 256, and the next letter times this. That's just a way of combining all three letters into one big number. So now I have one number. This big number is an encoding of the string high. And now I just encrypt that number. You encrypt things by taking them to the encryption key E mod n. So that's this, y is x to the E mod n. So this is my plain text, 4745505. I encrypt it. That's my ciphertext, that long string. So I can send that over an insecure channel like the internet, and nobody can read it unless they have the decryption key, which is up here. And to decrypt it, you take that number y to the D mod n. And it's taking forever because I'm trying to take this number, which is some huge number, billions, to this number, which is like trillions, and that's going to take forever. So I have to cancel that and use a faster exponentiation routine. Now, if I really wanted to take this number to that number and get the full value, I would have to wait forever. But I don't really want that. I'm going to take it modulus n. So since I can do it modulus n, there are shortcuts. And that's what happens here. That's what the PAL function does. Y to the D mod n can be calculated much more efficiently because it doesn't keep growing to a huge value. You can keep on using the modular property to trim it down to a small size as you go through the steps. So this function will calculate it efficiently. And now I get my original number back, 4745505. So that's the plain text. Here is the plain text. Here's the ciphertext. And here's the plain text again. And so I went from plain text to ciphertext by taking it to the E. And I went from the ciphertext to the plain text by taking that to the D. So that's the encryption key and that's the decryption key. And that's how RSA works. And so to convert it back to readable text, you can take the part of it that has been multiplied by 256 twice, that's the first letter, and the part of it has been multiplied once, that's the second letter, and that's the third letter. Another thing you could do, by the way, is you could just take the hex of it, there, and that's the first letter in hex, the second letter in hex, the third letter in hex. It amounts to exactly the same thing. So if I open up another terminal and do man ASCII, this is another way to do this encoding that might be more transparent. Let's see, let me make this fit on the screen better. All right, there's my number, and I just want to have man ASCII over here. All right, and that's octal. Here's the hexadecimal set. So I have 48, 69, 21. 48 is H, 69 is I, 21 is exclamation point. So that's another way to get this. That's all that's going on here. All right, so then you got some challenges. Extending this stuff to do. So that's the summary of how that one works.